Section 16.7 for Cut Poly or 16.8 for Pasadena, depending on which school you're attending, talks about Stokes Theorem. Stokes Theorem talks about a surface that's oriented, and this surface is smooth, piecewise smooth, surface having a smooth boundary C with positive orientation. We call first positive orientation, this negative orientation. Let vector field F have continuous partial derivative, at least the first order, on an open region containing C. Then, this, if you recall, this is our work. The line integral along C of F dot dr is, and this is what we just figured out in the previous section. So, you're also aware or familiar with this being curl of F dot N d rho or ds, and we derived that last time. So if I'm given the description of C as R of U and V, then there it is. And if I'm given the description of C as Z equal f of xy, recall that we said G to be Z minus f of xy. So basically you get 0 on one side, everything else on the other side, and that's the gradient that you take. And of course the curl of f, we all know what that is. We just did that. That is del cross of f. And that's pretty much all we need to do in this section, but there is one catch. I want to read that theorem again and make sure that you see it. Once I get a surface going, so this surface Z equal 4, 1, 2, 3, 4, it's going to cross at 2 and negative 2. Notice the shape of the surface doesn't matter. The surface S is right there. What matters is the boundary of C. So we want the boundary curve. This is based on the boundary. So how does that work? And this area is based on that boundary right there. So this is counterclockwise viewed from above. That means it is positive orientation. Okay, very good. So how do we going to set that? Well, it says verify Stokes theorem. What does that mean? Do both of those. Do this, do that. Well, how does that work? If I want to go for a single, well, I know how to do that. I know that R of t is, what is it? X squared plus y squared equal 4. Twice the cosine of t, twice the sine of t, and a 0, because that's on the floor. And this is the description of this C. So the closed integral of f dot dr across C is going to equal the integral from 0 to 2 pi. Actually, let's move downwards. Of what? Negative y, that's negative twice the sine of t, twice the cosine of t, and 0 cubed, which is 0, dotted with dr. What's the derivative of that? Negative twice the sine of t, twice the cosine of t, and a 0, dt. And that would be the integral from 0 to 2 pi, and let's see what that is. That is 4 the sine squared of t plus 4 the cosine squared of t, all dt. And that would be the integral from 0 to 2 pi of 4 times 1. So that is 4 times t evaluated from 0 to 2 pi. So that is 4 times 2 pi, which is 8 pi. There it is. And if we want to verify it, well, we want to figure out what's the double integral over S of curl of F dotted with oriented surface ds. That turns out to be circulation. Well, that is the double integral over the region D. The region D is right there. It's a circle. I'll play with that in a minute. But what's the curl of f? Curl of f is ijk, partial with respect to x, partial with respect to y, partial with respect to z, and I have a negative y, an x, and a z cubed. And that would be partial that's a 0, that's 0. Partial with respect to x, that's a 0 as well. And 1 minus a negative 1 plus 1, that's 2. So this is 0, 0, 2. And here I notice that the description is really, G is defined by moving everything to one side or this to it doesn't really matter, it's up to you. So that is z plus x squared plus y squared minus 4 equal to 0, because you want it to be bigger than or equal to 0, right? At all times. So that does it. Okay, what's the partial, what's the gradient of that? That is 2x, 2y, and a 1, dA. That is the double integral of 0 plus a 2 dA. That is 2 times the area of a circle. Isn't that what this d is? Well, what's the area of a circle? Pi times the radius squared. What's the radius? The radius is 2. Wouldn't that be 2 times 4 pi, which is 8 pi? So both of those work out perfectly. Now what? Now we're just going to use the actual theorem, and you're going to see the problem we picked right now worked really nicely. Oh boy, worked really nicely. But once I get to the next problems, I'll point out how things will work differently. So use Stokes theorem to evaluate the integral. It's up to you. You could use a line integral if you wish. You could use the double. Keep in mind how these things work. If I decided to look at I thought it was the same problem for some reason. So I'm looking at, it looks very close to the one we just did, right? So let's say 3. It's a hemisphere. Right? Z is bigger than or equal. Again, we're only interested in the surrounding. So how do you want to do this? Well, it's up to you. However you like. I could say, well, you know what? Find the double. I could go for the single. It says use Stokes theorem any way you like. So if you want to go by the line integral, you're welcome to do that. That's the integral. 0 to 2 pi again. And this is going to be also, it's a 3. That's the only difference, right? R of t is going to be 3 cosine of t, 3 sine of t, and a 0 because we're looking on the floor, right? T varies between 0 to pi. That will work. So I could say this is 9 sine of t, negative 9 cosine of t, and 9, no, that's 3 times 0. That's 0. Dotted would be r, negative 3 the sine of t, 3 the cosine of t, and a 0 dt. That will change soon. So that would be the integral from 0 to 2 pi of negative 27 the sine squared of t minus 27 the cosine squared of t dt, and you could proceed. Or you could use the other. It really doesn't matter how you do this. It's up to you. For now, we're dealing with very basic curve C. Now when I get to the next problem, things are slightly different. When I look at this, I'm looking at If both are 0, we have a 4. If both are 0, we have a 2. And 8/5, 1 and a... So we're looking at this. Now here you'll notice, C is the boundary. Did they say on all of those? Yeah, okay, they did say this is circulation, F counterclockwise from viewed from above. So all of these are positive, unless they tell you otherwise. So the deal is, when you look from the top, the only thing you see is, in the first octant, the only thing you see is the surrounding, right there. That point. Well, if you glance at this and you really want to do it, a line integral of that you need, if you really think about it, it's the line, what is the line? 4, 2. So it is this triangular region. Well, if you're going to do the C, then you're going to do C1, C2, C3. Do you remember that? Or you could say, well, the integral along C of f dot dr right? That's going to equal the double integral of what? Well, it's much easier to run a double integral. Why is that? Because you could say, well, look, x runs from 0 to 4. And y runs from 0. And this has an intercept of 2 and a slope of 2 down 4 to the right, negative 1/2 x plus 2. Right? That's simple. What's left? Well, I need the curl of f. And that's where the busy work is. Curl of f is the partial with respect to, that's a 0. The partial will be 0. That's 0 as well. Wow. And that is a negative 2x plus 1. So if I take that, 0, 0, negative 2x plus 1, dot it with, again, I have the equation set up. You could move the 8. Constant's not going to mean much. That's your g. And what is the gradient of g? So this is the curl of f. And this is the gradient of g. That is 245 dA. That is 0 plus 0. That is negative 10x plus 5. This is a lot nicer than you finding C1, C2, C3 and breaking this into 3 separate integrals and combining and doing all of that work. But it's up to you how you want to do this. And how about this problem? And how does that work? Well, I need is the intersection of the cylinder, x squared plus y squared equal 1. That's one of those. And, oh, it's positive. Okay, so that's good. And one of those. So what is it? It's the intersection of the two. And wouldn't the intersection actually be that circular part? So that is C. C is actually going to be bound by this. X squared plus y squared equals a 1. And that would mean I will take the line integral of f dot dr and I'll get the double integral over what? The curl of f. y, negative 1, and a z. And that is a 0, a 0, and an x. So that's going to be 0, 0, x, if I'm not mistaken. And I'm going to dot that with there it is, 2x, 2y, 2z dA. So that's simply the integral of 2x, but z is actually the square root of 25 minus x squared minus y squared. And I could do this 0 to 2 pi, 0 to 2, of 2 r cosine of theta, the square root of 25 minus r squared, r dr d theta. And there it is. I thought I had a rectangle, but I could be mistaken. Yeah, okay. Let me fix this. Actually, yeah, let me do that one. I'll do one more. That's okay. So the idea is if you do this over a rectangle, again, you really want to go for that double integral, and that's what they're going to go for. That's what they're going to ask you to do. So how about this problem? I have a cylinder with a radius of 2 that's running upwards, and then it's cut off by a plane. A plane starts at 3 minus y, so in the yz plane it's coming down, it's going to hit at 3, so something like this. Okay, there, so it's going to chop off that part where here it's flat, so something like this. Well, the bottom line is this is really the curve C. So it doesn't really matter how this works as long as it's not, something drastic. And then I can give you something drastic. So if I glance at this, I'll notice that, that's not bad. I could do this. The line integral of f dot d. I feel really bad about writing this. Let me write it properly. The way I wrote it, if you really follow what I'm asking, use the theorem to evaluate this. I should have said use the theorem to evaluate this part. Because if you go by the theorem, since the left implies the right, then you should use the line integral all the time. That's not what they're asking. Oh boy. That's what they're asking. And that's when you use the double integral. That's really what they want us to use. That would be the double integral of the curl of f dot the curl of g, right? Or the way they put it, ds, whatever makes you happy, or d rho, whatever makes you happy. And how does that work? Well, again, we're looking at a circle. We know how that works, but let's get the important part, or the tough part, out of the way. The curl of f, I, j, k, partial with respect to x, partial with respect to y, partial with respect to z. And we're looking at y, negative yz, and x squared y. That would be x squared minus y, and that would be 2xy minus 0, and it's negative, and the k component will be 0 minus 1. There we go. So that's going to be x squared minus y, negative 2xy, and negative 1. And I'm going to dot that with, and what do we have here? Again, we all had them this way. That is z plus y plus 3 equals 0. That's my g. So the gradient of g, that will be 0, 1, 1. dA, and that is the double integral. That's a 0. That's a negative 2xy minus 1. And we know how we're going to do this. We're going to say 0 to 2 pi, 0 to 2, negative twice, r squared, because that's r cosine of theta, r sine of theta. And you know that you could do this the sine of 2 theta if you wish. That makes it really a lot easier. And that's r d theta, right? r times r, that's negative 2r cubed. Nope, the 2 I need. Twice the sine cosine is the sine of 2 theta, and that is dr d theta. Many proceed. Really simple.